Welcome to this series of supply chain lectures. I'm Johannes Vermorel, and today I will be presenting Miami, a supply chain persona. A persona is a fictitious company, and in this case, it is a fictitious aviation MRO, that is to say, an aviation maintenance company. The goal for today's lecture is to gain a better understanding in aviation supply chains. Indeed, aviation supply chains are a fairly distinct form of supply chain that present a series of fairly, I would say, specific challenges. And one of my tenets for supply chain is to fall in love of the problem, not with the solution. And so I believe that if I look at what I would qualify as classic supply chain textbooks, that those textbooks are full of solutions, so recipes of some kind, that are intended to deliver improvements of some kind to supply chains. However, those solutions, I believe, are mostly wholly irrelevant when it comes to aviation challenges. And this lecture will help to clarify why. If you do not happen to work in an aviation supply chain, I still believe that today's lecture it is to be relevant for you as well. Indeed, due to the fact that aviation supply chain is so distinct, so characteristic, it magnifies all sorts of small differences that exist between verticals. And it can help you to crystallize a sort of understanding that helps you to understand what makes your supply chain really, really specific with regard to other supply chain, again, to assess the relevance of solutions as a prerequisite to even deliver any kind of improvement to your supply chain. So Miami is a fictitious company. We'll be getting back to that in a moment. But first, let's step back in time. And more specifically, let's step back in 1958. So in my views, 1958 is the debut of the Boeing 707. And it really marks the beginning of the modern aviation supply chain era. The 707 has all the attributes of modern airliners. I would say almost all the attributes. It is fundamentally a commercial jetliner with pressurized cabin, podded engines, and it is actually produced at scale. It was not the first pressurized cabin jetliner. The first one was actually the Comet in 1952 in terms of debut. However, due to a series of tragic accidents at the very beginning, the Comet never really, went to being, I would say, a dominant aircraft in the space. In particular, it did not dethrone the DC-3. And the 707 was not also the first commercial aircraft to use podded engines. The first jetliner to do that was actually the Carvel that started in 1955. Podded engines are, I would say, a key element of modern aircraft because the idea of the podded engine is that you can decouple the maintenance of the airframe and of the engine itself. And so from a supply chain perspective, it offers a great modularity. Suddenly, you can perform your maintenance operation much more conveniently by just immobilizing the aircraft, swapping the engine, and then keeping the aircraft up in the air while you take your time to do the engine maintenance. And then the last element was the scale, and that's where the 707 shines, is that we are talking of an aircraft that was produced, several hundreds of units, and that really led to the emergence of large-scale aviation supply chains. So the last innovation that you will find actually in modern aircraft that you do not find in the 707 is the fly-by-wire. And this did only happen in 1988 with essentially the Airbus A320, but that's another story. Essentially, I would say, fly-by-wire put aside, the A370 is really represent, I would say, the modern aviation supply chain. And so what we have is pretty much 60 years worth of the modern form of the aviation supply chain. And this industry has matured, it's fairly established. And so what we are going to cover in this lecture reflect, this very mature, established form of supply chain. And I believe that it will remain, it is actually quite efficient. And it will, I believe, remain as such for pretty much an extensive period of time and maybe, for a big part of the 21st century. And that's what we want to understand today. So to understand aviation supply chain, we need to start by understanding a little more about a modern jetliner. And actually, modern jetliners are pretty much marvels of human ingenuity. I mean, you can think of pretty much almost any kind of tech. It made its way one way or another to aircraft. Advanced electronics, composite materials, advanced engines, advanced motors, advanced batteries, advanced pretty much anything except maybe nuclear technologies. You will find that in an aircraft. And an aircraft includes a staggering number of parts. A small jetliner, I mean a business jet or a regional jet, we are talking of something like 250,000 parts. And if we go up to a jumbo jets, we are talking of several millions of parts. So obviously, for flight safety reasons, aircraft are fairly long-lived. An aircraft is going to live for something like 30 years. So an aircraft is very long-lived. Flight safety is paramount in modern supply chain, in modern aviation. And thus, all those parts are routinely inspected, revised, repaired, or changed, actually. And thus, the aircraft, it does not only include a large number of parts, it also includes a design that is extremely modular, precisely to make those maintenance operations as straightforward and as safe as possible and as economically efficient as possible. And this is reflected in the very design of the aircraft. And by the way, due to the fact that aircraft are so long-lived, there is an enormous portion of the aviation market that is not about producing the aircraft, but about maintaining the aircraft. And this is exactly the business of relevance for Miami, the persona that we are covering today. Miami deals with aircraft maintenance. So the story so far. This lecture is the first lecture of my third chapter in this whole series of supply chain lectures. So in my first chapter, I did present my views on supply chain, both as a field of study and as a practice. And what we have seen was that supply chain is essentially a collection of wicked problems, by opposition to tame problems. So it's problems where you have adversarial behaviors, and thus most of, I would say, the naive, straightforward ways to work towards solutions, things that recipes of some kind that could deliver improvement to our supply chain just do not work. And so a great deal of attention has to be paid on the methodology. The methodology not only to achieve the results, but also the methodology that you need to even acquire the knowledge that is needed to support the rollout of whatever solution is intended for the improvement of your supply chain. And so in the second chapter, we covered a whole series of methodologies that are, I believe, suitable to the improvement of supply chains. And the very first methodology that we covered was supply chain personae, which deal with fictitious company, and we'll get back to that in a minute. And so today we are presenting, we did already present as part of the previous chapter, one personae that was Paris, a fashion retail network. And today, as the first lecture of this third chapter that is entirely dedicated to personae, we are presenting actually an aviation persona. So, supply chain, a quick definition that was introduced in the very first lecture of this series. I define, personally, supply chain as the mastery of optionality in presence of viability when managing the flow of physical goods. So, mastery of optionality, it means that to take decisions when you have options on the table. From an aviation perspective, let's say we have a part number, we decide to order one more unit for this part number. This is a decision. One unit for this part number, so it's very specific. And the other options were, well, to order no part numbers, that would be 0, 1, 2, 3, or up till infinity. Those were all the options. So that's the mastery of options. And obviously, you want to identify what is the best option in order to take a decision. This is what supply chain is about. And this should not be confused with, let's say, logistics, operation, compliance, all sorts of things that are critically important. I'm not denying their importance, but they are not according to the definition that I propose, supply chain problem. Supply chain is really about the decision-making process of all the things that may or may not happen in your supply chain to deliver what sort of service you want to deliver. And so a persona is a fictitious company. So you might think, why fictitious? Well, this point was covered in the very first lecture of the second chapter, which entirely deals about supply chain persona. But as a tiny brief recap, case studies in supply chain do not work for a very simple reason. It's a conflict of interest. When a case study is produced, everybody has a vetted interest in concluding that the solution is very, very good and delivers tons of value for the supply chain. And obviously, as a result, it's not overly surprising, 99% plus of the case studies that are available out there conclude that whatever solution has been studied delivers dramatic improvement to the supply chain. I'm very skeptical about that, especially in mature industries like the one of interest today for aviation supply chains. And when you look at what is happening in the industry, you would see that most solutions are actually tentative solutions and that there is it's hit or miss, and we are certainly not at 99% hit rates in delivering improvement in those supply chains. So essentially, case studies are glorified infomercial, and thus as an alternative, we do a persona, and a persona is essentially a fictitious company, and we only focus on the problem itself. So today, as part of this lecture, I'm focusing really on defining what is the problem that we are actually trying to solve for aviation. That's the key understanding, and there were some rejection criteria that are listed in the previous lecture. The key idea when we think of a persona is that we want to make this persona to reverse the asymmetry that exists in a case study. In a case study, it is very easy to produce, but it is actually near impossible to disprove or debunk. And the persona, we want the opposite. We want something that is very difficult to produce, but actually fairly straightforward to reject. And I'm just listing the rejection criteria. Again, back to the previous lecture to see the full detail. So Miami. Miami is a fictitious aviation MRO. So MRO stands for maintenance, repair, overhaul. So this is a company dedicated to the maintenance of aircraft fleets. And this company is based near Miami, hence the name I picked for this fictitious company. Let's assume that it was a company that emerged in the 70s with the rise of the commercial aviation. I gathered some key figures for you to gain some understanding, of this company. Essentially, the bulk of the business of Miami is long-term maintenance contracts that are closed with airlines. So essentially, the bulk of the business of Miami is to basically serve airlines, to serve the maintenance needs of airlines, and so they're through long-term contracts. And typically, that's going to be multi-year contracts up to a decade, and that's about $1 billion per year. That's just the ballpark. And the profitability exists, but it's relatively thin, 5% EBITDA. And in order to achieve that, Miami needs about $500 million worth of stock, which is quite sizable. Indeed, aerospace equipment, aerospace parts, and it's mostly the bulk of that is actually comprised of repairable parts called rotables, and they are fairly expensive. And so as a fringe activity, I mean, it's a small activity, Miami also operates a trading desk, an AOG desk. We will get back to those points, which is much smaller, $50 million, with a much higher profitability. And those represent an activity where Miami is basically trading parts to help other airlines that are not part of the pool, so companies that don't have like a long-term contract with Miami, or even competitors. And what we can see is that in terms of fleet serves, again, I'm giving you, orders of magnitude. We are talking of a company with, let's say, 1,000 aircraft being served, 10 different fleets. So fleets would represent different aircraft types. So there is a diversity of fleets to be supported. And the company operates 2 stores. One would be, let's say, in Fort Lauderdale. That would be the primary one, a secondary one near Seattle. And then on top of that, we would have like 50 MBKs. So MBKs are main base kits. They represent advanced location with each MBK has probably something like a few hundred SKUs. And that represents deported inventory that is made available to the airline clients to ease some kind of, I would say, routine local maintenance operations. And in total, we are talking of something like 250,000 distinct part numbers and something like 500,000 SKUs. So the complexity is very, very high. And so that's the business of Miami, is really smoothing out all this complexity on behalf of the airlines it serves. So the mission of Miami is to keep aircraft in the air at all time. So aircraft are very, very expensive pieces of equipment. As a ballpark, a typical jetliner, we can think that the order of magnitude is $100 million plus for the cost of one commercial jetliner, And so aircraft are expected to fly at all time. You want to have like a maximal asset utilization for your fleet. And so obviously flight safety is paramount, which means that whenever there is something that is not right with the aircraft is going to get grounded. And technically, this sort of incident is called an AOG, aircraft on ground. And the most common reason for getting an aircraft grounded is a very mundane reason. It's just that one part that is needed to perform a routine maintenance operation happened to be missing. And so when an aircraft gets grounded, it puts the entire flight schedule of the airline in jeopardy, because obviously all those flight schedules are dependent on one another. So if one aircraft gets delayed, you can have all the other aircraft get delayed, and then you need to find potentially alternative for passengers. So it can be you have a cascade of effects, and it can be very, very costly. As a rule of thumb, just as an order of magnitude, I estimate that typically a 737 getting grounded for an entire day would cost an airline something like $300,000 just because the aircraft gets grounded for a whole day. So obviously, if your aircraft gets grounded for an entire day just because a $50 screw is missing, that's a fairly expensive screw. So also that's why when you think about all the things that can ground an aircraft, it's the weakest link that matters. It doesn't matter whether your aircraft is missing an entire jet engine that costs multiple millions of dollars, or that it's missing one screw. It's just weakest link, and then the aircraft is going to get grounded. And that's why parts availability, is really paramount for the economic survival of airlines. But also, that explains why, for example, things like 99% service level don't really mean anything for aviation. You see, it's nowhere near sufficient. If again, we are talking of aircraft that includes literally thousands and thousands of distinct parts, if you have 1% chance to have a part that is missing, that you will end up with every single maintenance operation is going to end up with one or several parts being missing, and thus you will get an AOG at every single time. So the way you have to think availability is really about making sure that AOGs happens as infrequently as possible. So Miami, from an economic perspective, acts as a pool for all those airlines. So you see, the thing is, Miami holds about $500 million worth of inventory. But if every single airline had to maintain its own pool of parts, the sum of all those pools would be much more than the $500 million that Miami is keeping. So it's not like Miami leverage laws of large numbers, because in aviation it's always laws of small numbers, but nonetheless Miami leverage laws of larger numbers to have a much higher utilization. It's just because you don't need the same number of parts if you have like multiple airlines that consolidate all their stocks. And that's exactly the added economic value of Miami. At least that's a big part of it, is just asset mutualization. And so the demand for parts is pretty much proportional to the fleet size. Although it is fairly random, there is complex maintenance schedule, but there is a large amount of variability because some parts might be repaired, and it's very, very difficult to know ahead of time exactly what needs to be repaired. We'll get back to that in a minute. So in this presentation of this Aviation MRO, we are going to present first a first section that provides all the insight concerning the operations to understand what is happening on the ground and what sort of considerations are even applicable to aviation supply chains. And then we are going to have a look in a second section, a whole series of insight on the sort of decisions that need to be taken by the supply chain teams of Miami. And that's what really matters from a supply chain optimization perspective. So aircraft maintenance needs to be performed on time. And when a maintenance operation starts, it's really a matter, time is of the essence. Every minute counts. And indeed, if the aircraft is late, it's going to wreak havoc for all the flight schedules that are dependent on this one maintenance operation. And so when the aircraft arrive, what you get is the teams on the ground are going to, they know in advance a bit what they expect to do in terms of maintenance, but they don't know the exact conditions of the aircraft, and they are going to inspect, and so they are going to face what I call a random bill of material, a random bomb. Which is they just realize that the aircraft come in, they inspect, and then they realize the extent of all the things that need to be, changed. And thus, they don't get, as it is the case in the industry, a fixed deterministic bill of material where you know exactly what you need. Here, it will have a degree of indeterminism where you don't know exactly what you're going to need, so hence the random bomb. And as a consequence, teams on the ground are fairly aware of this, of those random fluctuations. So whenever a maintenance operation is about to start, the teams will have requested ahead of time quantities of equipment, of parts, that are greater to what they really think they will be needing. For example, if you think that you will need, most of the time you will need one part, but you might be needing two parts, you want to play it safe. You will be asking two parts every single time, and thus most of the time you will be returning one part unused. And just to give you an idea about the sort of magnitude of the phenomenon, I observed that casually for many MROs, about 1/3 of the inventory movements are actually returns of parts unused. So we are talking literally of teams that if they think they will be needing one, possibly two, they will always ask two and return one, and then you end up with roughly 1/3. So those flows are very important and need to be taken into account. Also, one very key element of understanding about the parts is the notion of a part can be serviceable or unserviceable. Indeed, there is a preservation of mass as far as aircraft are concerned. If you're mounting anything on an aircraft, then pretty much by definition, you had just been unmounting something just before doing that. You don't add mass over time to the aircraft. You preserve the mass. So if you mount something, it means that you've just probably just before, you had unmounted a component. And the idea is that fly gradiness, so if a part can be mounted on an aircraft and fly, this is what referred to as the part is serviceable. That means that it can be mounted. And typically, when a component or a part is dismounted from an aircraft, it becomes unserviceable. Not always, but most of the time, if it's unmounted, it's because it is now unserviceable and it must be inspected, revised, repaired, or maybe directly changed, actually. And so there's serviceable and unserviceable are very important. We'll be getting back to that later in this lecture. And then there is also a very, very important concept, which is the standard exchange. And that's really, it's really a matter of supply chain efficiency. So when the aircraft comes in, the aircraft is the ownership, the aircraft in full is the ownership of the airline. And suddenly you have the MRO that is starting the maintenance operation, and they unmount a component. This component belonged to the aircraft, so it was fundamentally the ownership of the airline company. And then the MRO is going to take a component of its own, a serviceable component. So it's this component is the property of the MRO. And this component is going to be mounted on the aircraft. So what do we have now? We have one aircraft which has one component that is the property of the MRO, and then we have an unserviceable piece of equipment that is in the hand of the MRO that is technically still the ownership of the airline. We could potentially decide that the aircraft is going to take off, and then a few weeks later it will going to get back to the MRO, and then we will swap again the components because we will have by that time repaired the component that was the original in the original possession of the airline. However, supply chain-wise, it is very, very inefficient. So it is much more efficient to proceed to a standard exchange, which is we have swapped the components, and then the component that was the property of the MRO, we are going to decide that now it's going to become the property of the airline, and the component that was the property of the airline is going to become the property of the MRO. That's the standard exchange. And then we have a problem. We have a problem because the component that gets swapped might have different value. Indeed, maybe the component that was in the aircraft was having a lifespan that was left. The component had 20,000 flight hours left in it. That was the value of the component in the aircraft. And the component that the MRO is mounting on the aircraft might be a component that has only 10,000 hours left in it. So you see, there is a swap, but those things are not exactly equal. One has twice as much flight hours left in it. And so there is the standard exchange is essentially a financial transaction where you do a swap of ownership, but you also take into account, I would say, the delta of value between the two equipments to take into account the fact that the equipments that are being swapped might not have the exact value. So you have to take that into account. And this process of standard exchange is very, very efficient because suddenly it means that we do this swap, and then the aircraft doesn't have to come back to kind of to reset the ownership of who is owning what. This is the standard exchange is literally taking advantage of that. And that the standard exchange is one of the pivotal elements that ensure the efficiency of a modern aviation supply chain. And by the way, it also means that, as far as the MRO is concerned, there is a constant inflow of materials, of part numbers that were never purchased in the first place by the MRO itself. And that's something that really complicates, and again, the supply chain, and we will be getting back to that later. So now let's have a look at aircraft parts, the tangible aspects of an aircraft parts. So first we have the class. The class is rotable or expendable. We have the two typical classes. So a rotable part is typically a part that is tracked at the serial number level. So it's serial inventory. So you don't know that you have 3 units for a given part number in stock. You literally know the whole series of serial numbers. And typically, rotables, although not always, but typically they are repairable, expensive repairable equipments. Again, aircraft are very, very long-lived. An aircraft is going to live something like 3 decades, but there are many equipments that are very long-lived as well. A part can live, more than a decade. And by the way, in this Miami persona, we can say that something like 90% of the inventory value possessed by Miami is actually rotables equipments. And then we have expendable equipments, things that when you just consume them to perform the maintenance operation, you can't repair them. They are just discarded after use or even consumed by the maintenance process. Then we have the essentiality. Essentiality really means how essential the part actually is for the aircraft to be able to take off. A no-go part means that the part is absolutely essential. The aircraft will not take off if this part is actually requested and unavailable. A go part means that the aircraft can take off. It's typically going to be something that is non-essential, maybe a piece of cabin equipment, so the aircraft can take off. This is much less critical. And then go if means that the aircraft can take off but under conditions and restrictions. And that would be, for example, if you have, let's say, for example, a piece of toilet equipment. If you have one less toilet that is available in an aircraft, the aircraft may take off. However, it has to take off with a reduced passenger capacity that is reduced by the percentage of the toilets that are not available in the aircraft. So if you have half of your toilets that are unavailable, you have half the passenger capacity. And then you have, for parts, you have every part pretty much have a life cycle associated to it. So a part has typically flight hours, or many parts of the rotable parts at least, have flight hours in them and flight cycles. By the way, flight cycle is the aircraft taking off and landing. That constitutes a cycle. And now, and obviously, when a part is reaching its end of I would say, of lifespan, it needs to be changed, which means that it is of interest to make sure that you change a lot of parts at any point of time when you have the chance to do a maintenance operation, because otherwise, if you just have one part that kind of expire halfway through your maintenance schedule, it means that you're going to ground the aircraft to change this one part and then be done with it. So that's why you typically want to have some safety nets just to make sure that there is no part that triggered like a forced maintenance operation for the aircraft. And then you have the compatibility. And that's something where you need to think in terms of function. So there is a part in an aircraft, it fulfills a function. It can be, for example, a pump. So the pump fulfills a function. However, there are typically multiple OEMs, original equipment manufacturers, that can provide equivalent parts, but with distinct part numbers, that can fulfill this function. And so when you think in terms of aircraft maintenance, you have typically to think in terms of function. I have a need for a function. Do I have a part that fulfills this function? And here it can get fairly tricky. The simple situation is the two-way compatibility. So you have two parts that are completely interchangeable. So that means that part A can be used whenever part B is needed and vice versa. However, it is also possible that you can have one-way compatibility. And that typically happens when you have multiple standards. And the idea is that you have parts of the old standards, you have parts with the new standards, and the OEM says, or the aircraft manufacturer says, or the flight authority says, somebody in the loop, in the loop is saying that an aircraft that flies with the old standard can have parts either from the old standard or the new standard being installed on the aircraft. However, if a part from the new standard gets installed on the aircraft, you've got a ratchet effect. Click. Suddenly, it is not authorized to basically mount a part of the old standard anymore. And that's kind of tricky. And so you have to think that suddenly, if you mount, when you have like one-way compatibilities, it means that whenever you mount a part of the new standard on an aircraft that was equipped with the old standard, you are kind of extinguishing the demand, the future demand for the parts of the old standard on this aircraft. Again, keep that in mind for what we are going to do later on in this lecture when it comes to supply chain decisions. And then unit of measures. That can get, again, this aviation, everything is like, can be super complicated. You can have things that are in inches, just units, one part, two parts extra, just like it is regularly done in many verticals. But you can have also rolls, you can have surface measure, and the idea is just to give you a taste of the sort of problem. I won't be delving too much into that, although we can discuss that in the questions. Is that if you have, let's say, 50 meters worth of cable, it's not the same way. It's not the same thing if you have one cable of 50 meters that you can cut, or if you have in your stock 5 cables of 10 meters each. You see, so you need to take into account exactly the fine composition of the stock, and also you might actually be buying the stock in one unit of measure and be consuming the stock according to another unit of measure, and that can really complicate the situation. Just for those of you who are not very familiar with aerospace equipment, anything that can fly is typically very, very expensive. Not only just because it's certified, but just because there are tons of extra requirements. For example, if you look at just a simple computer keyboard, just the one that you use, to type for your computer, a computer keyboard in an aircraft might be costing something like $20,000. And you might think it's extravagant, but the reality is that this computer keyboard that can fly in the cockpit of the aircraft, maybe it's a sort of keyboard that if there is a fire and this keyboard starts burning, it's not going to emit smoke that is going to instantaneously kill the pilots. You see, that's all sort of requirements that you would not think of when it's, so anything that flies tends to come with a long list of very specific safety requirements that just make those equipments much more expensive. And then we are looking at very, very small series and the cost. So we are talking of fairly, fairly expensive parts mostly. And then we have all the intangible elements that are associated to parts. First, there is all the things that ensure the flight gradiness of parts. So you have tons of authorities that are involved in basically granting all the authorization so that a part can actually fly mounted on an aircraft. I'm not going to list all of that, all of them, but the idea is that companies like Miami's have typically really need to have excellent traceability, complete auditability of everything for all the parts. So they know exactly all the maintenance operations that have ever happened on the part. And the reason is that if there is any doubt, you don't have the complete traceability, then basically the part is basically worth its weight of metal, which means nothing. It's really all the elements that make this part flight grade that gives all the value to the part. A part comes with, especially if it's repairable, so one of those rotable I was mentioning, comes typically with a component maintenance manual, which is sold by the OEM, and it can get quite tricky because sometimes the same part that is repairable can be acquired with or without the component maintenance manual, which means that there are situations where if the part was acquired without the manual, although technically it could be repaired, it's not necessarily feasible because the manual wasn't acquired in the first place. So that complicates many decisions. And then prices. When you think in terms of price of parts, the aviation market is fairly complex, and you don't have like public quotations for every single part number in the market. And so you end up with a certain degree of opacity in this market. And so for a company like Miami, there is a great deal of amount of effort involved to establish something that would be the fair market value of parts. That represent, sort of things that you could expect if you were to sell or buy the part in regular condition. But the price really depends on the conditions. You have the list price, the price that is typically advertised by the OEM. Although this price can be quite high, it don't really reflect the sort of negotiated condition that a company as large as Miami can actually obtain if they are not too much in a hurry. And on the other side, if you really have an emergency, maybe you will have to purchase the part at the AOG price, and that can be much, much higher. Just to give you a sort of order of magnitude, a part might be worth, the list price might be $20,000, the fair market value might be $15,000, and the AOG price might be something like $30,000. So you see that the price can vary greatly depending on the circumstances. And so also, the idea is that so far I've been discussing of aircraft parts, but the reality is that while some parts are completely standalone and can be, changed and maintained, in isolation, very frequently the things of interest are units, modular units. And so that would be, for example, the APU, auxiliary power unit. That's a whole block. And all those units have been introduced in the aircraft precisely to improve the efficiency of the maintenance operation and the supply chain that is associated with those maintenance operations. So the idea is that you can unmount a whole block and this block is going to contain, potentially thousands of parts, but you don't deal with every single part. You deal with a block that you can rapidly unmount, and then you can remount a new block a new unit in the aircraft. And then you typically have the line replaceable units that are the units that can be changed in a line. That is like the first line of repair, and then you have the SRU, the shop replaceable units that are typically the second line of repairs, and those sort of reparation happens in the back shops that represent more complex elements, I would say, maintenance-wise. So now that we have seen all of that, let's have a look at the actual supply chain decisions that are needed to operate all these, to pilot all those maintenance operations for Miami. The first key concept that I would like to introduce is the float. So the naive notion of stock on hand as far aviation supply chain is concerned is vastly misleading. Just to give you an idea, first, what you have on hand is kind of irrelevant. It is what is on hand and serviceable that matter, because you might have parts that are on hand, but they are unserviceable. So what really matters is first on hand and serviceable, but also is it really a good indicator of anything? No, not really. Because from a, I would say, classic mainstream supply chain perspective, you would say, oh, if my stock on hand is at zero, then I need to reorder. But in aviation, not at all. Because maybe you have plenty of parts that are just undergoing maintenance. And so you know that you have a large number of parts that are going to flow back to your store once they are repaired. And maybe you have a lot of parts that are going to flow back just because of those returns unused very quickly. And keep in mind that when you buy a part, especially a rotable, you're stuck with it for a very, very long time. The aircraft lasts for something like 30 years, as we have seen, but a typical rotable can last for a decade or more. Which means that when you buy a part, you're stuck with that, and the part is going to be needed, mounted, unmounted, repaired, and it goes in loops and loops. So the float is essentially the number of parts that are not attached to any aircraft. And this is a number that characterizes the sort of extra inventory that is available to conduct the maintenance operation. And that's a number, the float. So, and just to give you an idea, if you could repair instantaneously the parts, then you would not need, you could have a float at zero, because you would unmount a component from an aircraft, repair the component on the spot instantaneously, and remount the component right back in the aircraft. So you will not need any float. However, repairing parts takes time. That's called, by the way, the total amount of time between the request and the renewed availability of the serviceable piece of equipment is called the turnaround time, the TAT. So essentially, the float is very much dependent on that you need to have to achieve a certain level of part availability to serve your fleet, is dependent on the number of aircraft that you serve. The aircraft are basically the one that generate the demand for parts, but it is also vaguely proportional to the size of your fleet. The more aircraft, the more parts you will need, but it's also only vaguely proportional to your turnaround time. And if you have a turnaround time that is much longer, it means that you need to maintain a lot more parts in your float. And so the float is very interesting because this number represents your long-term commitment, and it's kind of an invariant with regard to all the sort of short-term operations that happen all the time in your aviation supply chain. For example, the float is do not differentiate between the fact that parts are serviceable or unserviceable, because this is essentially a temporary state of the parts. A part that is unserviceable is just going to get repaired and becomes serviceable again, assuming we are talking of a repairable part in the first place. Also, it is you have lease and borrows. So you might actually be leasing parts for a couple of weeks, couple of months to one of your competitors. So that means that you don't see the part in your stock, but when you want to think, do I have enough or not? You have to think that you have a lease that is going to expire, soon, and thus you know that a part is going to fly back into your circuit. And same thing with the borrows. Maybe you have parts that you can see in your stock, but actually, and you can see that in your stock you have plenty of parts, but actually this is not the case, because actually you have borrowed parts from competitors and you're going to give them back. Again, the float gives you the sort of long-term vision of where do you stand in terms of part ownership of parts that are not readily attached to aircraft that you actually serve. And also, the standard exchange complicates the situation as well. Because you have to think that in order to characterize, your float, you can count your float, but then you have to ask your question, is this float kind of, I would say, too much or too little? And as I said, it depends on the demand, so the size of your fleet, but also it depends on the turnaround time. So the turnaround time is the time it takes between the moment when a part is requested, so there is a request for a part number that should be serviceable in order to be served, and the time that the component goes back to you. By the way, a standard exchange will most likely happen during the operation of the aircraft maintenance. So you ship a part number, it is swapped with another part number, and this other part numbers is cycling back to be repaid, and then to finally get back to your store with a renewed serviceability. And you want to compute the turnaround time, but you have a problem. You have a problem is that when the standard exchange happens, you've got a mismatch between two part numbers, and typically in most maintenance operations, people do not keep track of the pairing. So a part number is mounted, a part number is unmounted, and you don't keep track from an IT perspective of the pairing. So what you see when you try to compute your turnaround time, it can be very difficult, because what you see is a constant streams of part numbers being sent to your clients or potentially to your own facilities, a constant stream of part numbers that are, that are expected away from your store, and you see a constant streams of parts that are received back from, again, your clients and your own facilities. And the pairing can be lost, and that can be very, very tricky. And so, in a nutshell, just to summarize all of that, the float really characterizes the sort of buffer that you have, the long-term buffer that you have to actually efficiently serve your fleet and avoid the AOGs. Now, let's go down to the actual decisions that we are making for an aviation supply chain. The first decision that you need to take is you have an incoming request for a part number. So there is a request for the part number. The question is, what are you going to serve? You could say, obviously, because you might have, among your stock that is eligible, so that's going to be the serviceable part numbers, so the serviceable parts that have the same part numbers, you might have multiple units that you can serve. And here, there are in practice, there is a lot of extra complications with regard to the sort of contractual agreement that Miami would have with every single airline it serves. I don't have the time in this lecture to go into this degree of details. You, again, ask questions during the question time if you want to have more specifics, but I'm putting that aside. So there would be, contractual constraints. But putting that aside, the question would be, I have multiple serial numbers that I can use. Which one I am going to use? You might think that I'm going to serve first the serial number that has the highest number of flight hours and flight cycle left in it. Indeed, it is of interest, if you're about to mount a part on an aircraft, that you mount a part that has as much flight hours and flight cycle left in it, so that this part doesn't trigger an excess of maintenance operation in the future. So basically, you're anticipating that by doing that, you can reduce the amount of maintenance operation that you will have to do for this airline, for this aircraft in the future. But also, you have another problem, is that many parts, not all the parts, but some of the parts, have a shelf life, which means that, for example, every 6 months, the parts need to be inspected, revised, and potentially repaired to some extent, even if it wasn't mounted on an aircraft. So that means that although you don't necessarily want to do first in, first out, but because you want to pick parts that have that typically have the highest level of shelf life, of flight hours in them, you don't necessarily want to leave on the side forever the same part, because then you can incur cost just because you wait for the parts to expire, and that you have to do a maintenance operation on a part that is not even flying. Thus, and then you also have the fact that, remember, I described parts actually serve a specific function. So you're going to have a request for a part number, and this part number is going to match the part numbers that is presently in the aircraft. But you're not necessarily forced to serve the same part number. You can actually serve a compatible part number, and that can be, that can be a very high interest, especially if among your client airlines you have variations in your contractual obligations, and you have some airlines that says, when you serve me and ask for a part number, I want this part number to be served and this part number only. That might be a deal that you've negotiated with one airline. But if you've negotiated another deal with another airline that says, when I request this part number, you can serve me with either this part number or a strictly equivalent compatible other part number, that might be an option. So you have to really cherry pick in your stock the right part to be served. And this decision needs to be done every single time that you're servicing every single part. By the way, beware of the one-way compatibilities, because as you see the old standard, new standard I was discussing about, whenever you're servicing a part of the new standard, you are extinguishing a portion of the future demand that you could expect for the old standard. And that can be kind of good. If you're running out of stock with regard to the old standard, that can be a smart move to start upgrading your fleet toward the new standard. But if you prematurely migrate your fleet to the new standard, what you could be left is a big pile of dead stock, which are all the part of the old standard that you cannot mount on any aircraft anymore. And this is of your own making because you did trigger this transition. Now, the second decision would be, so we have just seen how to serve the parts. The second decision would be sizing the float. And that's typically done through investment and divestment. So here we are really talking about controlling the float. And the question that should be asked is that if you have only $1 to spend, $1 extra to spend on your inventory, which is the part number that gives you the biggest bang for your buck? What is the one part that you should buy, for per dollar, that gives you the biggest reduction of AOG incident, per year, considering the present state of your fleet? This is the way you want to really drive your investment. You want to invest in the one part that will gives you the biggest reduction of AOG incidents. And then once you've invested in this part, if you have any money left, you can actually decide to buy a second part, and then a third part, etc., etc. So you will proceed, and you have really to think of dollars per reduced per amount of AOG incident reduced per year. That's the key metric of incident. Again, a company like Miami is in the business of really avoiding, on behalf of its clients, any kind of AOG incident. They want to keep the aircraft flying at all time. So that's why it's very, very important to optimize, the investment. And again, once you invest in a part, you are kind of stuck with it. And by the way, you have to think in terms of wise investment. You have to take into account that all the alternatives that exist. For example, when I say per dollar invested, I would say you have to think per dollar compared to the alternatives. Because, for example, if you have a part where if you face an AOG incident, you know that this part is super heavily available in the market. So maybe the AOG price that I was discussing in the very beginning is actually very, very low. It might actually be very, very close in certain circumstances. The AOG price might almost be equal to the fair market value. So in this sort of situation, what you want to assess is not only the amount of extra AOG that you're solving, but the extra AOGs that you're solving compared to an alternative option, which is to not buy the part, so not to include this extra unit in your float, and just take into account that when the day comes, and if you face an AOG incident, you will have options that you will be able to exercise at a later date. And if those options are essentially almost identical to purchasing ahead of time, those options might be much better because at least you're not stuck with it ahead of time, because maybe this AOG situation will never happen. So if it's the case, then you've literally spared yourself the entire spending for the parts. So that needs to be taken into account. Also, as the part is going to be very, very long-lived, you have to take into account the future evolution of your fleet. If you're buying a part right now that is going to live and remain functional for, let's say, 2 decades, if this part is, for example, only of use for the 747, well, there might not be, any 747 flying in the sky 20 years from now. So obviously, you need to take into account that the evolution of your fleets and whether this part is only going to be needed for, I would say, old fleets or new fleets is also an element of primary importance to assess, how much value does this part actually bring to your float. Now, you have the opposite decision. So you can actually buy a part, but you can also sell a part. And then you have to do the exact same sort of reasoning, but just the other way around. So if you could establish, a list of what is the number one part that you should actually buy, you can think of what is the part that you could sell that would give you the largest amount of dollars back for the least amount of extra increase of EOG incidents. Indeed, as soon as you sell a part, you're going to increase your risk, at least marginally, of facing an EOG incident. So you want to think that if you have one part that you can sell, you want to think of the part that will bring you the largest amount of dollars per AOG incident that you will actually that you would actually cause. So that's exactly the same sort of reasoning, but just the other the tail of the list, if you want, when you start thinking what contributes the most to improve my quality of service, what contributes the least per dollar. And the idea is that in aviation, you have trusted marketplaces, kind of the eBay, if you want, of aircraft parts. One of them is, for example, ALS. It's very well known. And those marketplaces are highly trusted. They are operated by trusted players, so that the way where it is possible to actually resell one of the parts. And thus, the idea is that with this investment divestment, Miami, by doing those operations continuously, can make sure that the composition of the float it has remains completely synchronized with the need of the fleets. Indeed, there will be aircraft that enter the fleet and exit the fleets routinely. We are talking of 1,000 aircraft, so pretty much every single week there will be aircraft entering or leaving the fleet. And also the aircraft themselves are aging over time. So that their need change. It's slow, but it changes over time, and thus the composition of the floats need to accommodate the fact that the need of the fleets that you serve are slowly changing over time, and that's exactly done with those investment and divestment decisions. By the way, there is also this decision needs to be done for the MBKs. I've not discussed that a lot, but fundamentally, the MBKs are the main base kits. It's like advanced inventory location that are typically on sites along with the airlines, and they are for those stocks are for light maintenance operation that can be done sometimes by the airlines themselves. And they need to have the same sort of reasoning, but just applied at the MBK level. And by the way, as a final note, is that whenever a scrap happens, so a scrap is a part is repairable, but sometimes you attempt a repair and the repair is not successful. So the part after repair, doesn't pass all the quality control, and thus the part has failed the repair. It needs to be scrapped. Scrapped are interesting in terms of investment, because if you have a part that has a high scrap rate, it means that every time a part gets scrapped, it undo your investment decision, which is kind of good. It means that if you invest on parts that gets heavily scrapped, you're not taking as much risk as if you are investing on parts that never get scrapped, because whenever scrap happens, it's going to undo your previous investment decision. That's something to take into account, and this thing obviously has a negative effect on the parts that you would like to divest. Now, we have the repairs to manage. So remember, we have parts that are components that are unmounted, they are unserviceable, they are flowing back to you, and now you need to decide what you're going to do with those. The first thing is that whenever a component, a unit, as I was describing, is getting repaired, this unit is also going to have a random bill of material situation. So you will face a random bound as well. So you know that the component is getting back to you. you kind of expect what sort of parts you will need to complete the maintenance of this unit. But then when you get the unit itself and you open the unit, you discover the fine print of what is actually needed. So this sort of random bomb does not only happen in the first frontal maintenance operation that I was describing, it also happens when you are organizing the repairs of the components. And that's where it gets very tricky in terms of turnaround time. I described, the sort of relationship that exists between the float and the turnaround time is that whenever a part is missing to conduct a repair, it means that the repair is going to be delayed until you receive the part to conduct the repair. So it's interesting because I described that if you have a longer turnaround time, then you need typically a bigger float to address that. But so bigger float means bigger stock. But if you have more stock, it can mean a better quality of service to operate your repairs, and thus it will in turn reduce the turnaround time. So you see, you have all sort of coupling all over the place that really complicates the picture, and yet it's very, very important because those turnaround times are very essential. So first, you need to decide what is the next repair. Imagine you have plenty of parts that you can repair. Your shop has a limited repair capacity, so it needs to prioritize to schedule the order of the repairs. There, you need to think in terms of what is the most urgent. Obviously, if you have a part where accidentally you have no serviceable part left, then it is probably a case for a high priority repair. So you need to take into account the exact spot condition of your store in terms of serviceable parts to prioritize the parts where you are most critically, I would say, in danger of facing an AOG situation. So that should prioritize the repairs. Same thing, and then so so the parts, there is this prioritization that needs to happen, and then there is also the opportunity of not repairing the parts. As a rule of thumb, repairing a part can cost something like 1/3 of the original cost of the equipment. Obviously, this numbers varies enormously depending on the sort of component we are looking at, but as a ballpark, I would say estimate 1/3 is a typical estimate. That kind of makes sense. And so there are situations where it makes sense to not repair a part and to keep a stock of unserviceable parts. This can be, for example, of interest if you, for example, in the pandemic in 2020, there is a drastic drop in activity, then maybe you don't need temporarily to repair all the parts. You can just postpone the repairs and save the cash. So postponing the repair is ultimately, you will probably want to do the repair so that you can get the full value of the part that you have. But if you just postpone the repair, it can save a lot of cash in the short term, and that's a very reversible mechanism that is at your disposal. So now and that will be the last element of the decisions. There is the asset management. So as I said, availability, flight safety is paramount, and just second is that you want to keep aircraft in the air at all times. So you have what could happen when a part is missing is that you have an AOG incident. And the asset management division is typically dedicated to deal with those situations. And what a company like Miami, a large MRO, has is typically an AOG desk. So that's a desk that is going to be open 24/7, and then any other actors, aviation actors, can actually submit a request for quotation asking for a part number to be provided under AOG conditions. So those companies, those actors can either be airlines that are not part of the pool served by Miami, so they don't have like a general contractual agreement to forward their demand directly to Miami. But it can also be actually competitors of Miami that have a need for their own need. And here the idea is that whenever there is an incoming request for a part number, the question is essentially twofold. I mean, assuming that Miami has at least one unit, one serviceable unit at its disposal, then the question is twofold. First is, what is the cost incurred by Miami if it actually serves this part to whoever is requesting the parts? Because indeed, if you serve the part, that means that you have one part less available for your own operation. So you might be solving an AOG situation for one of your competitors, but you're taking the risk of creating an AOG situation for yourself. So the first element of answering this question is to assess in dollars what is the risk that I create by doing that. So just the cost side of the equation. And then the second part of the question is the markup. How much, so you have the cost, how much risk you incur, and then how much margin are you willing to take? And here, this is basically an AOG desk. It works with pretty much short-lived auctions. So the company that is requesting the part number is probably going to send this RFQ to a dozen of companies, and within something like 2 hours, 3 hours, they will collect the answers that they got, and they will take the decision among those very trusted players going for the cheapest option, or taking into account the fact that some actors might be actually much closer than others. I mean, they can literally be in the same airport. So here, in terms of markup, so the first element of the analysis was the cost, what sort of extra risk you create for your own supply chain. The other one is the markup, knowing that the bigger the markup, the smaller the odds that your offer gets ultimately selected. So it's some sort of auction mechanism where you want to have a markup that is, that maximize the sort of volume of margin that you're going to make, knowing that it's an auction game being played. You want to be just, $1 below the other competitors, but not more, because then you're just leaving money on the table. And by the way, again, when a part number is requested, your answer doesn't necessarily have to be a part number. It can actually be another part number that just belongs to the same function. Again, compatibility work, and if an airline is facing an AOG situation, they might be willing to take for not the same part number, but just a compatible part number, granted that it's completely trusted and has complete, I would say, flight readiness attached to it. Okay, so we are nearing the end of this lecture, but there is still plenty of other elements. We could go on for another hour or so, or maybe a couple of hours. I'm just going to mention briefly other elements that I haven't even touched so far. Marketplaces. Marketplaces are really of high interest. They exist in the aviation supply chains. They are fairly active. Again, components can live for a very long time, so you can sell secondhand. You can resell your equipment, buy secondhand equipment. All of that is operated by highly trusted actors, which means that from your float perspective, your investment, divestment, you can have opportunities. For example, maybe a part is usually not top of your list in terms of investment list, you see, because it doesn't deliver the biggest bang for the bucks. But if there is a spot opportunity to buy a part on the cheap, then suddenly a part which was not really interesting becomes very interesting just because somebody posted on the marketplace the same part number at half the usual price for any reason. And for example, one of the reasons why you have sometimes, large fluctuation for the price of parts is that sometimes aircraft get dismantled. So you have an entire aircraft, and then when they take over the aircraft, they completely, dismount the aircraft and try to salvage all the values. When an aircraft gets decommissioned, typically there are plenty of parts in the aircraft that are not nearly as old as the aircraft. There are plenty of parts that might have been mounted just a few months ago. So there might be plenty of equipment that is still fairly new, even if the aircraft is fairly old. And all these equipment is going to go directly to the marketplace, and that's going to, to be an influx of extra supply, and that can lead to large variation of the price. And so there is opportunities, spot opportunities to buy parts on the cheap. Then you have retrofits. Retrofits, so again, fly safety is paramount. So if an OEM, original equipment manufacturer, has any kind of suspicion of having a safety problem with one of the equipment, they might actually trigger a retrofit. And the retrofit is literally for every single part that was ever pushed to the market, they are going to push a second one and say, we want the old part to be returned to us, or all the guarantees are void. And the idea is that the OEM takes the initiative of pushing new parts that should replace for all the fleets, all the existing parts. For every single part that was ever pushed, you push another one. But so that means that supply chain-wise, if you try to analyze the sort of flows that happen in your aviation supply chains, retrofits, you will see inventory movements, but they are not pool. Those inventory movements were not parts being requested. It can be something that is pushed by the OEM itself, and that can completely confuse all the sort of demand analysis that you want to make for the parts. And it can also complicate your life later on, because when an OEM does a retrofit, it means that it's going to push at one point of time fresh parts to the entire fleet, and thus it's going to synchronize the maintenance schedule of all those parts across all the aircraft that are eligible for these retrofits, which means that when parts are going to be in need of repair, all those parts will be completely synchronized, which wasn't typically the case, as typically aircraft gets introduced gradually, so there is a lot of spread in terms of maintenance schedule. Then you can have grounded fleets. This is infrequent, but it still happens. Every 2 or 3 years, one fleet gets grounded, typically for safety reasons. The last one was probably the 737 MAX, and so when you have that, you have kind of an extinguishing. The demand for an entire segment of your aircraft gets extinguished from one day to the next, and there are a lot of commonalities between the aircraft, so that there are complex relationships between the sort of aircraft that stop flying and the parts that will be requested in the future. But grounded aircraft really complicates the picture. And then finally, jet engines. So jet engines, I mean, aviation is like super specific. I believe that for the audience that is familiar with other verticals, they would probably agree with me that it's very unlike many other verticals, but jet engines is like a world inside the world. So it is a world of its own inside aviation, and it has tons of very, very specific complexities that I will not be touching today unless there are specific questions about that. Now finally, just like aircraft, it's all about cycling, takeoff and landing. This is like, and you want to be able to repeat this cycle endlessly and flawlessly. That's what aviation supply chain are about. And aviation supply chains are all about loops. So instead, while most of the other supply chains are about a forward supply chain that goes from the producer to the consumer with a series of hubs, plant, and then warehouse, and then store, and then consumer. In supply chain, in aviation supply chains, parts, which represent those rotable parts representing the vast majority of the value, just circle. And mastering those loops is essentially the essence of the aviation supply chain. And what we have seen is that the concepts like float are the embodiments of the fact that all the parts are looping all the times. By the way, I've discussed about the aviation supply chains, but there is the terms also of aerospace, and that's the broader segment. Typically in aerospace, you have aviation, and then you have also helicopters, so aircraft and helicopters. Helicopters are managed pretty much the same of what I've described today, although they are just a tiny fraction of the aircraft market, something like 5% or so. So commercial aircraft are really, really massively dominant. And then if we look at space equipment, well, space is basically not reusable yet. However, if companies like SpaceX really succeed at developing the space industry at scale with reusable equipment, because obviously there is no such thing really as I would say a space supply chain, because with traditional rockets you just fire them and then they're consumed, and you very infrequently fire rockets. But if you start having rockets that are reusable and that you fire them all the time and you get them back, then my bet will be that the sort of supply chain strategies that will be put in place will be essentially similar to the one that exists today for the aviation. And so, so my take is that what you have seen today will be probably one form of supply chain that will remain, prevalent for during probably a big portion of the 21st century, and that this aerospace supply chain for probably, the decades to come might actually start to include, space equipment on top of aircraft and helicopters. Okay, so let's have a look at the questions. So one question is there a difference between the float and the pool? So fundamentally, the float is an invariant. That is a metric. That is a metric that characterizes the activity of the MRO for a function or a part number. And you want this number to be really invariant to all the sort of super mundane short-term fluctuations. Typically, when you describe the pool, you are more referring to the fact that what is just routinely available in stock in the store. There is not, again, I would say the pool is more like the economic entity, the business unit with all the stuff that belongs to the business unit. The float is really a numerical artifact that is actually quite tricky to compute, in practice. It is a constructed number, and usually it is even, getting an accurate depiction of the float is typically a very non-trivial undertaking. And yet, this is a very, very important number because most if you don't correctly characterize your float, you can't take, investment and divestment, correct investment and divestment decisions. Again, the pool is more like the economic vision where it's not really decision oriented. It's just a matter of a business perspective. Does it belong to me? Does it not? Does it belong to someone else? Okay, a question from Alexei Tikhonov. How are random bombs managed from a transactional perspective, ERP, WMS? They can't work with randomness usually, or is the meaning of a bomb created on demand just before the service procedure? Well, it turned out that I believe that, Alexei, you did actually answer the question in your later suggestion. This is that. Indeed, the random bomb do not exist at all in the ERP. It doesn't exist at all in the WMS. It's just that people do the maintenance operation, and then they list, as they are doing the maintenance operation, they just list all the stuff that they use. Typically using barcode readers and whatnot, they are going to scan all the things that they use, beep, 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 beep. And this constitutes the bomb. So you will not, those random bombs, they are not really verified. What you will get is there is this maintenance operation, and here was the list of the part that I did consume. And then you can think of them as random bombs, although if you look in the ERP or WMS or MRP, you will not find a table that contains random bombs. You will just see operations and list of parts introduced. And by the way, I really differentiate random bomb, which is random is the phenomenon that happens, and then you have probabilistic bomb, which is a specific modelization perspective that, for example, Lokad adopts. So Lokad, when we face random bombs, we adopt a probabilistic perspective, but that's a modeling perspective. So we have the phenomenon, random bomb, and then we have the modelization approach, which is probabilistic bomb, which is the way we start to think of the phenomenon from a statistical perspective. There would be other non-probabilistic approach to actually deal with that. So a question from BlondBoy75 is the cost of conducting service on aircraft mostly outweighing the benefit of deflating remaining hour cycle on existing spares. The cost of conducting service on aircraft and heuristics to pick the part with the most hours or cycle left. Well, it really, really depends on the sort of parts we're talking of. Remember, in an aircraft, you have some parts that are worth, very little. So maybe you have like a tiny part that is a tiny pump, and it's just worth $2,000. And this part, if it's, if it's nearing this end of life, you will need to ground the aircraft to actually perform a maintenance operation. So maybe for a part that is only $2,000, you really want to avoid this sort of situation. But then, if we are talking of a jet engine, so a jet engine, just to give you a ballpark, the one that gets under the wing, the order of magnitude is $10 million or above, for just one engine. So if you're talking of a jet engine as a whole, well, it's a completely different game. So really, you have several orders of magnitude. So I would say that to your answer, the answer to your question is, well, it really depends on the value of the unit or the value of the part are being considered. And obviously, the more expensive and ultra critical the part is, the more you can afford to put the part on an aircraft with a small reserve of flight hours, just because it makes more economical sense. But again, there are plenty of other considerations, just a general consideration. And typically, you have to think that in aerospace, the price of parts are, really are very, very high. And that what really matters is not whether you put one person or 3% to do the maintenance. It's not what costs the most money. What costs the most money is that if the maintenance do not really happen on time, then you wreak havoc in the flight schedule of the entire airline, and that is like super, super costly. So yes, you want to have things that are highly, highly productive, but that's the modular design of the aircraft, where it's very straightforward to mount and unmount. It's as straightforward as possible to safely mount and unmount components while ensuring complete flight readiness of the aircraft. But fundamentally, what dominates are the cost of the rotable equipments and the cost of the AOGs when they happen. That's really the figures that really dominates. The rest is important, but it's typically much smaller. Vijay Jadav, sorry for probably pronouncing your name completely wrong. Is there any organization which is pulling out the inventory of spares requires for MROs of aircraft held by various operators? Yes, there are. There are companies that are literally where their only value is just a pool. So that literally their economical value is literally to have the parts and let other companies to do all the repairs. One of them, for example, one of those companies happened to be a long-time client of Lokad, would be Spare in Germany. So Spare was created as a joint venture between Lufthansa Technik and Air France Industries for the launch of the Airbus A380, the jumbo jet, the largest aircraft ever produced by Airbus. And thus, because they had this new aircraft being created, they created literally a company that nowadays they are initially acted literally as a pool of parts to mutualize the consumption of those two companies, Lufthansa Technik and Air France Industries. And at least initially, they were literally just a pool. So they were just, holding up stock for the benefit of those two companies, Air France Industries and Lufthansa Technik, which are two very large European MROs with plenty of repair capabilities of their own. So yes, it exists, and it kind of makes sense, and it does happen. Sometimes, so Alexei Tikhonov, sometimes you don't know if a part becomes serviceable again after the repair, how to compute the probability of becoming serviceable again. True, that's typically what we call the scrap rate. So the scrap rate is literally the probability that the part will be scrapped after the repair. As usual, we look at historical data. So that's something that helps tremendously, that gives you sort of a baseline. Now, where it can get very tricky is that some parts get repaired very, very infrequently. So when you have a part that get only repaired, even when looking at a super large MRO like Miami that I described today, if you have a part that only gets repaired something like twice a year, and this part has only been, in the market for just, let's say, 2 years, because 2 years ago it underwent a retrofit. So this part is kind of new, and the only thing that you see is the new parts. For the old parts, you had the scrap rates, but now you see the new parts, and for this new part, you only have like 4 points. Well, it's and you have not even seen any scrap so far. It is very, very difficult. So the idea is that, without getting too technical, is that there are plenty of the parts in the aircraft. There are plenty of hierarchies, you know, the ATAP chapters that would give you, for example, the sort of type of where does the part is located in the aircraft, and then you can have tons of characteristics. Is it like a pneumatic part? Is it an electronic part? Is it a part that is static, that is mobile, or whatever? And so, using the characteristic of a part, even if you have not seen, you know, a lot of data on this part specifically, you can kind of refine your estimate of scrap rate by looking at parts that have the same sort of mechanical characteristics, for example. So blown by 75, that's a follow-up question. Does the existence of units change the cost of conducting service, since you know other parts will need service? So any parts with cycle left in excess or excess is fine. Okay, so does the existence of units change the way you conduct service? Absolutely, absolutely. And for example, again, parts are very, very modular. So sometimes you have the opportunity to decide, for example, if you have, let's say, a very large unit, very complex, you can just open the unit and to change a subunit that is itself a major component and decide to be done with it, and so that you can accelerate, you know, the repair. The other way would be you open the total unit, and then you open the subunit, and in the subunit you only change the part that you actually need. So you see, units have been designed from precisely a modularity perspective, a maintenance perspective. It's those units are in place in aircraft to precisely give you tons of options when it comes to repairs. Maybe you want to be super swift. You will actually change the jet engine entirely and be done with it. Or maybe you will just change a few parts in the engine, or maybe you will do something in between. Modularization is very, very key, because we have to deal with an enormous number of parts, so we need to have plenty of alternatives. So in terms of, by the way, in terms of things that I did not discuss, is that when you need a part, you also have the option to cannibalize a unit that exists. So you need just this part, you don't have any of those parts left, but you know that you have a unit that actually contains the part. So you can actually open this unit, cannibalize the part, and then you will have a hole that you will fill up later on. But that, you know, there are tons of trade-off, and due to the fact that parts are very, very expensive, usually you can even afford having an engineer spending half an hour to think about the problem just for one part. Because if the part is worth, you know, half $100,000, it's completely reasonable to have somebody, you know, to spend literally half an hour, 1 hour, just to get the right decision for this one part. And that's where aviation supply chain is very different from, let's say, other industries where you would never spend, you know, an hour, a full hour of engineering thinking time just for one part. Okay, so as maybe a last question, Vijay Jadhav, I would like to understand the perspective of upgrade and change of part numbers and making the inventory redundant for future use. So indeed, the idea is that that is, so I'm not exactly sure to understand your question completely correctly, but the idea is that when you invest in a part, you will be stuck, especially it's a rotable, it's a long-lived part, you know, it's going to live 1 decade, 2 decades. You really want to look far into the future, and you want to think in terms of what will be the fleet of the future that you will be serving. So, for example, if you're buying, if you have a small section of your fleet right now that need a part, and it's a very small section, but you know that this part is going to be, for example, needed by the Airbus A350, which is, you know, a rising fleet, you kind of guess that you can reasonably guess that there will be a lot of those aircraft. You know, there is a bit of gambling involved. You know, you don't know the future perfectly, but it is a very modern aircraft, and you can guess that there will be plenty of those aircraft in the future flying, and thus you buy those parts in advance. In advance, in the sense you buy the parts to serve the small portion of your fleet now, but you think that it's very profitable and that's a wise investment, you know, in terms of modification of your float, because you expect that the airline contracts that you will sign in the future will include plenty of aircraft of the future that might not be flying yet, but they will be flying, you know, 10 years from now. So yes, you need to think about the fact that there is an evolution, and most of the evolution in the aviation industry happens slowly, and you have, you know, the sort of evolution years in advance. For example, I was mentioning, you know, the A380, the jumbo jet from Airbus. People knew years in advance that basically the business was not going too great for the A320, and so the number of units that were ordered by airlines were kind of stagnating till there was a point that there was not enough, and Airbus decided to discontinue, you know, the future production of this aircraft. And so you know that as far the parts that are only, you know, for the A380, you have a very clear view of what sort of numbers of A380 will be flying in the future. The only uncertainty is whether some aircraft might actually decommission and disassemble earlier. That's the only remaining uncertainty. So there is tons of knowledge that you have, but the good news is that this knowledge is typically at a very, very granular level, such as the type of aircraft, the type of fleets. So you don't necessarily need to have a specific, you know, knowledge at the part number level. Okay, so this is it for today. The next lecture will be 3 weeks from now. It will be same day of the week, Wednesday, same times of the day, 3 p.m. Time of Paris. And I will be discussing modern computers for modern supply chains. The idea is that we will probably alternate one persona with one lecture of auxiliary sciences. So the next series of my next lecture will be a lecture on an auxiliary science, so something that is not exactly part of supply chain, but it's very much needed, the sort of knowledge that is very much needed if you want to bring, you know, state-of-the-art optimization to your supply chain. See you next time.